It's a pleasure to have Sanjib Sabhapandit as our speaker today. Sanjib has a strong link to our department, and many of you know him. He did his PhD here with Deepak, and then he went to the University of Wisconsin to work with Susan Coppersmith. Afterwards, he spent a few years in Paris before joining Raman Research Institute, where he is a full professor in the theoretical physics group. Sanjib's work spans around disordered systems, non-equilibrium statistical mechanics, stochastic processes. Particularly, he has done impactful work on the extreme value statistics. In recent years, he has been working on the active matter dynamics and large deviations. So today he will tell us more about his work on the theory of large deviations and its relevance in the statistical mechanics. So with that, over to you, Sanjib.
Okay, thank you, Teddy, for this introduction, and also thank you for inviting me for this talk. So today I'm going to talk about these large deviations in non-equilibrium systems. So before I start, let me just thank my collaborators. So some of this work is done with Abhishek and Anupam, and some part of the work was done with Arnav and Deepak Gupta. So both of them were my students, and they are now postdocs elsewhere. And Arnav is going to join IIT, I think, quite soon. Okay, so I'm going to start with a brief introduction to large deviations. So I'm sure many of you have already heard about large deviations, and some of you have probably are also working on this. But nevertheless, let me just start with the elementary concept of large deviation to set the stage for the rest of the talk. So after this brief introduction, I'm going to talk about large deviation in non-equilibrium systems. So of course, large deviation is a very large subject, and okay, even large deviation in non-equilibrium subjects is also quite large. So I'm going to focus on a very specific aspects of this, and basically I'm going to talk about large deviations in the context of thermodynamics of small systems that are kept out of equilibrium by external driving. So I'm going to focus on three aspects of large deviations. First one is, of course, the large deviations of the fluctuation of additive observables, like this work done in a given amount of time, or heat flow in a given amount of time, entropy production, etc. Okay. So after that, I'm going to talk about the symmetry properties of the probabilities of entropy productions. So in particular, when you have forgotten to take into account some degrees of freedom, for example, when you are computing the entropy production, and how does it affect the symmetry properties. And finally, very briefly, I'm going to talk about the ratio observables, which is basically the ratio of two time additive quantities like this efficiency, for example, which is the ratio of, let's say, work and the heat. Okay. So in this plan, let me just start with this elementary thing. What is a large deviation? Okay. So let me try to explain it with a very simple example. So imagine that you just close all your doors and windows and seal it such that air cannot go out of your room, and also it cannot come in. So there is a certain number of air molecules in the room, and you divide it by the volume that gives you a global density. But now you want to know what is this density of air in that room. So you go and tell your theory student that, okay, go and measure this density and tell me what is this density. Of course, this student is not going to go around the room and counting all the molecules of air in the room. So instead, what he and she is going to do, take a small volume and then count the number of molecules within that volume and divide it by the volume that gives you a density. But as you know that from your undergrad experiments, this thing that, okay, you just don't do the experiment only once. So you repeat these experiments many times, and each time you do the experiment, it gives you a density. So rho 1, rho 2, this basically varies from sample to sample. So after you have this density, so you find the average. So what you'll probably find is that this average is equal to your global density. Okay, but there will be, of course, fluctuation from sample to sample. And what about these fluctuations? So as you already know, the typical fluctuations are Gaussian. Okay, so typical in the sense that, okay, so if you look at the fluctuation in the scale of 1 by square root of the small volume V, so those fluctuations are given by Gaussian distribution. So precisely what I mean is that, so if you look at this rho minus rho average and you multiply it by square root of V, so this quantity in the limit of V very large, so it goes to this Gaussian distribution. Okay, so this distribution describes these typical fluctuations. But what about the large fluctuation? So you can ask, what is the probability that there are only very few particles in that volume where you are counting these particles? Or what is the probability that there are large number of particles, which is not basically much greater than from this, different from this rho bar, much greater than this 1 by square root of V. So these are these large fluctuations. So how do you describe these fluctuations? So these fluctuations are not described by this Gaussian distribution. Okay, so if it is an equilibrium gas, of course, then, so you know that the number of particles within this small volume V, so this fluctuation that, or in fact, probability distribution of this number of particles, you can just write it as a ratio of these partition functions. So this is the partition function for the full volume, and this is the partition function for this outside volume, and this is the partition function for the inside volume. So I'm assuming that this gas has short range interaction, so that the interaction between this particle and this outside particles from this outside volume, the contribution from that is basically proportional to the exponential of this surface area, where this term, this is the smallest term, goes like the exponential of this volume. Okay, so I'm going to neglect this term basically. Okay. So now, given this partition function, of course, you can write down the free energy, and then when this volume where you are measuring, counting your number of particles, if it is much smaller than the size of this room, so what you will find is that, okay, this number distribution of the number has this form. So it's a exponential is in exponential time minus volume times this scaling function, which is a function of the density. So it's number times the volume. And the scaling function, which is the function of the density, so this is, in this case, is given by this exactly. So you can just find out. And this function is called the large deviation function or the rate function. Okay. So of course, as you expect that the small fluctuation should be Gaussian, this is what everyday
Sanjib, can I ask
yes,
you a question?
sure.
Yeah. So if you go back to the previous slide.
Yes.
Yeah, so I'm just trying to track the dimensions here. So this function of f of n over v, n over v, of course, is a dimension full quantity.
Yeah, 1 over v. Yes.
So the so you are not trying to invent some dimensionless quantity whose function you're talking about.
No. So
function here.
No. No. You can make it dimensionless. Then you have to basically divide this volume by something else. So this function is basically the dimension of 1 over volume in this case.
Right.
So the volume,
So in equation in equation 2, the right hand side. Okay, so the left hand side has a dimension of energy, and the right hand side. Yeah, so this function of n over v, is it a power? I mean, it cannot be a polynomial, right? Because, or it cannot be some complicated function. Because
no, you will see. No, it can be simply a function where there's a prefactor which is just 1 over volume, and then it's a. So you can have a 1 over volume prefactor. So we'll see. Basically, we'll see that. See this rho bar. As you see that rho bar is a dimension of 1 over volume, right?
Right. Yeah.
So it can be like rho bar times function of n by v, basically.
Yeah. Right. So there is a beta also, which is in the I huge. So which also.
Yeah.
So the energy.
So
that I agree. But this small f has to be a kind of a monomial, right? I mean, because n over v is a dimension full quantity. So the only function that I can write of a dimension full quantity is a monomial, just a single power.
So actually, Gautam, I'll just give a simple example and it will become very clear actually there.
Right. Yeah, thanks.
Okay. So let's just do an explicit calculation here. Okay. So let's just look at the case of an ideal gas. Okay. Right. So in this ideal case, your partition function is just volume to the power n by n factorial. Okay. So I have not considered the whatever the term coming from the kinetic energy, because they just cancels in the numerator and denominator. So this is just the position part, and because each particle is basically has an accessible volume v, and there are n particles, so it's just v to the power n divided by n factorial, because these are just an indistinguishable particle. Okay, so in this case, what you will see is that, okay, your beta times f of rho, which appears in your large deviation function, is just given by rho log rho minus rho. So again, okay, you might ask, okay, why this rho is 1 over volume? How can you taking a log of a 1 over volume? So you should see that, okay, this volume, when I saying it, there is already a, I should have in fact take volume to the power n divided by some other volume, h cos to the power something, but those I have basically neglected it.
So this is the dimensionless volume, meaning that volume measured in terms of the lattice cutoff.
Yeah, exactly.
Okay.
Exactly. Yeah. So I have neglected that your whatever the minimal cell size in terms of h cross, that I have neglected.
Okay, thank you. Thank you.
Yeah. So then in this case, basically what you find is that basically your this function is okay, as I said, that it should have this form, and in this case this large deviation function is exactly given by this, okay, for this ideal gas. And this is this orange curve or red curve I'm plotting here, and this is the quadratic form. So you see that near rho equal to rho bar, they of course agree quite well, but so rho equal to rho bar is this typical value. Okay, around this it quite well. So that means that around this typical value, so Gaussian distribution is basically a good description. But if you go far away from there, so they differ quite distinct, and far away from this typical fluctuation, this large deviation function actually, or the large deviation form of the probability distribution function, provides the description of this problem. Okay, so to summarize what I said, that okay, you are looking at this probability distribution of some observable, in this case it's number, or it can be density, but okay, and observable, and this for a given volume v. So you have these two extensive, one extensive variable and one extensive parameter. So it has this form which says that okay, exponential of minus some extensive parameter and a scaling function of this ratio of these extensive quantities, so which is an intensive quantity. Okay. So is this form generic, and if it is generic, where does it come from? Okay. So to understand this, so let's just go back to this problem for this ideal gas. So where this student was counting this number of particles within this small volume. So now let's just look at this volume in a big scale. So you just zoom in and imagine that you have basically divided this volume into very small cells of infinitesimal cells of volume dV. Okay, so clearly the total number of particles with this volume is just the sum of the number of particles within each cells. So this n is basically the sum of the number of particles within each cell. So what is the probability that there is one particle in the ith cell, because these particles are independent, they don't interact, so you just pick each particle independently. So this is just rho bar times dV, because rho bar is the global density. So what's the probability of having two particles? It's proportional to dV square. And when dV becomes very small in this limit, keeping this volume fixed, so those terms becomes irrelevant. They basically, the contribution from those terms go to 0. So the probability of having, so basically when dV becomes very small, so you have either 0 particle or 1 particle. So probability of having 0 particle is 1 particle is rho bar dV, and probability of having 1 particle is just 0 particle is 1 minus rho bar dV. Of course, given this, you can go ahead and solve this problem exactly, and what you will find is that okay, P of n is just a Poisson distribution. But today I'm not interested to find out the exact form of this distribution. So what I am interested in this particular form. This number you can actually write it as sum of some random variables. In this case, it takes value 1 and 0. Okay, so basically I'm interested in a observable like this, which is a sum of random variables, which in the previous example takes value 1 and 0, but you can just think of it like some general random variables. So these are independent random variables. Independent random variables, these are drawn from the same distribution. So these are IID random variables. So I can either describe this variable by giving its probability density function, or I can equivalently describe it by the generating function of these random variables. So given this generating function, since these are independent random variables, so the exponential of the lambda s, the expectation value of this, so this is the generating function of s. So this factorizes into the individual generating functions, because exponential of the s is just product of these individual terms, and since they are independent, I can just evaluate them independently. And since each term is generating function is exponential of mu of lambda, so it's just exponential of n times mu of lambda. So given this, so I can write down what is the probability distribution function by this integral. So this is essentially a Fourier transform in the complex plane. You just rotate by pi by 2, okay? And you just substitute this from here, and then you see that you rearrange, because this is minus lambda s, so you divide it by n and you take a n outside. Here there is already a n there, so you take it outside, so you have this form. So once you have this integral of this kind, and when n is very large, so you scale s with n, so that's of order 1. So you know how to solve this integral, all of us know. So basically what we do is that we do a saddle point calculation. So when you do a saddle point calculation, it says that, okay, it should be exponential of minus this n times some function of s by n. And this function is basically nothing but just minimum of this function along the path of the steepest descent. So it's basically the function at the saddle point. So which is basically saddle point is given by this equation. So it basically what it says that the probability distribution of the sum of these random variables has this peculiar form, is exponential of minus n times some scaling function of s by n, and this scaling function is known as the large deviation function. Okay, this scaling function is of course not universal; it varies from problem to problem. But what is universal is this form, and of course, what is other thing universal is that if you expand this around the typical value, it has this quadratic form, which should give you the Gaussian distribution. Okay, so of course, if you have a now. So this is for if the variables are independent, but of course, if you have a correlation among these variables, okay, things can be different. And nevertheless, if the correlation is not too strong, if the correlation is mild, what I mean is that, okay, there's a certain correlation length, and beyond which your correlation function decays to 0 exponentially. Okay, so this can be either an integral or a sum. Okay, it doesn't matter that much. So you're either looking at the integral or a sum, basically. So then what you can do is, okay, so you have certain interval, let's say between 0 and n, and you have a correlation length, which is your xi, so which you assume to be much, much smaller than n. So you're looking, or you are taking n, which is much, much larger than this correlation length. So you can basically divide this thing in some multiple of xi, or 10 times xi, or 100 times xi, it doesn't matter. And then you basically sum within these blocks. So then this sum, you can just write it as a block sum. So y is just a sum within this block. And now since this correlation falls off, so you can basically treat these y variables as if they are independent. And if you treat them as independent, I mean, using what I have told about independent variables, so what you find is that, okay, I mean, what you expect is that, okay, e to the power lambda s, this generating function, should have this form, where exponential of mu lambda is just the generating function of this variable y. Okay, and given this form, so you can write down this large division form, where your large division function is related to this mu of lambda by this Legendre transform. Basically, just do the saddle point. So, but, okay, I should caution you here. So although this correlation is weak, although it's decaying exponentially, since these are not independent, there can be a prefactor here. And usually you neglect this prefactor as a subletting term, and this is what gives you the large division function. So this you can do as long as your prefactor is analytic. But if this prefactor contains singularities, you can no longer throw away saying that this is a subleading term, and that contributes to your large deviation function. Okay, so then in that case, the large deviation function is not given by this Legendre transform, but it will be determined by this prefactor. And that's a take-home message. Basically, okay, when you have this kind of problem, it's not enough to compute just this mu of lambda, but you have to also compute this prefactor to at least to find out whether, I mean, it's prefactor singular or it's analytic function. If it is singular, then this is not how you get the large deviation function. So this is a take-home message. I mean, it's going to be a take-home message, which we'll see in some examples. Okay. So with this, let me just start my actually main part of the talk on large deviation in out of equilibrium system in the context of thermodynamics of small systems. So if there are any question, I can take. Otherwise, I'll just go ahead.
Sir, just one doubt. The block sums you had, they'll also be correlated, right? I mean,
yeah. So it's like this renormalize. No? So okay. So imagine that these are like some 100 times xi or 1000 times xi. You are blocking them. There'll be, of course, small amount of correlation, but you expect that this correlation will be around the boundary, and most of the term will be contributed by the volume. If let's assume this is not xi, but let's say some 100 times xi or 1000 times xi.
Okay, yeah, I understand. Thanks.
It's just like the same way you found it when you write down this free energy, you just throw away the term which is proportional to the exponential in the surface area, right?
Yes.
Okay. Yeah. But what we are going to see is that it's not the case, and actually, I mean, this correlation matters. Okay. So I'm not saying that, okay, you can actually do that. So this is a naive expectation, what we saw from the example I was giving in terms of these free energies. But what we are going to see is that actually sometimes this is not the case. Okay. So now, so I'm going to talk about large division in microscopic system. But before going there, so let's just look at the prototypical example of non-equilibrium system. So it is a heat conductor connected two heat reservoirs. One is at hot temperature, one is at cold temperatures. So you just connect by an iron bar or something like that. So you know that if you connect them, the heat will flow from the hot reservoir to the cold reservoir. And if Q amount of heat flows in a given time t from the hot reservoir to the cold reservoirs, so you can find out what is the entropy production in the reservoirs, because these reservoirs are always in equilibrium. And if Q amount of heat is coming out of this reservoir, then minus Q times the temperature of this reservoir is the entropy change in this reservoir. The same amount of heat is you are adding to this reservoir. So this is Q divided by the temperature of this. So this is the entropy change in this reservoir. And as you see that this is a positive quantity because the TH is greater than TC. Okay. So this is a example of entropy production in non-equilibrium systems. Okay. So now let's take the same setup and just think of it like, okay, instead of this your big iron bar, it's a microscopic thermal conductor, some nano wire or something. Okay. So again, heat will flow across this thermal conductor. But now, because it's a small system, so although on the average heat flows from the hot system to the hot bath to the cold bath, there'll be fluctuations. So it's no longer a deterministic quantity. So Q in a given amount of time is a fluctuating quantity. So it has a distribution. Okay. So one of the questions you might want to ask is what is the nature of these fluctuations? So you expect that, okay, because this Q is some additive quantity, because it's just a total amount of heat flow in a given time. So T is your extensive parameter now. So it should have this large deviation form. The question is, what is this I of Q? Also notice that you can have negative fluctuations. So negative fluctuation means that you might find events where heat is actually flowing from the cold reservoirs to the hot reservoirs. Okay, these things have non-zero probability, and although they are rare, so you might it happens, and you might want to ask, okay, how rare are these negative fluctuations? Okay. So in this respect, in this context, basically there is something called fluctuation theorem, so which is actually a theorem for entropy production, where you can actually show it exactly. But since, okay, heat and work, entropy, these are similar quantities, okay, you might expect that, okay, it also has a similar form. And if this P follows this fluctuation theorem, what it says that these negative fluctuations are related to the positive fluctuation by this one. So it's exponentially rare compared to the positive fluctuation. And this relation you can also write down in terms of the large division. So this is a large division statement of this relation. So in terms of the large division, it's basically the symmetry relation of this large division function. So this is something, again, you want to see, okay, whether this, I mean, this kind of relation is true for heat or it's only true for entropy production. And we'll see that actually, okay, I mean, like for heat or for work, etc., there are instances where this relation need not be true, actually, okay? And if it is not true, then, okay, I mean, this is only way to find out this rare events, and you want to find out how rare these events. See, the advantage of this relation is that once you have this relation, because although this might be very rare, so the positive need not be very rare. For example, this might be the typical fluctuation which is given by the Gaussian, and once you have this probability here, you might find out the probability distribution here just by this relation. Okay, provided this relation is true. So this is something, again, you might want to see. I mean, when it breaks down. Okay.
So, Sanjib, is there an understanding which kind of microscopic dynamics would give rise to such kind of fluctuation relations, and is there any criteria?
Yeah, so okay, so one criteria is, of course, if so I think what I understand is that if you have a system with a finite state space, right, so in that case it's always satisfies, and this whatever your prefactor is always analytic. But if you have a system is your state space is infinite, for example, in this case, continuous case, so then it's not clear what, I mean, for a specific system, you can see that in certain regimes it satisfies, and in certain regimes it's not satisfies. But there is no, I think, specific criteria. You can just say that, just looking at the system, say that, okay, here it will be satisfied and here it will not be satisfied.
So there is two parts. One, you have a large deviation form, and the second is the large deviation function following the symmetry. Are you talking about?
Exactly. The large deviation function following the symmetry.
Okay, and that you're saying.
So when large division, when will large division follow function follow symmetry, it's not a priori obvious.
I see. Okay.
But on the other hand, it's, I think, fairly obvious that this kind of thing will follow the large division form. That even we'll just see from this example, basically. Okay.
Okay. Okay.
So the large division form is obvious, but this symmetry is not obvious, basically.
I see. Okay. Thanks.
Okay. So therefore, that's why it's useful to look at examples and see when it is satisfied and when it is not satisfied. And with Anupam and Abhishek, so we looked at this Ising model for basically heat conduction, so which is basically harmonic chain. So this at the two ends you attach to two baths, so at different temperature, TL and TR. And also you can, these baths can have different friction coefficients, gamma L and gamma R. So it need not be just the next nearest neighbor this thing. So you can also have long distance connection, but still these are harmonic. Or you can have a pinning, but okay, as long as these are harmonic, it's fine. So you can write down this Hamiltonian, which says basically the kinetic energy time and the potential energy term. And this phi LM basically says how these two different coordinates are coupled. Okay. So given this Hamiltonian, you can write down the Lange-Bach equation. So this part is just the Hamiltonian dynamics. Okay. And then this part basically models the interaction with the bath. So it's just interaction at the two ends. And so these etas are basically, so eta L and eta R. So these are Gaussian noise. And then they basically follows this fluctuation distribution relation with gammas. Okay. So this basically
sorry, Sanjib, can I ask? So yes, this phi LMs are not nearest neighbors, right? I mean, they are.
It need not be nearest neighbor. So as long as basically you have this form, so it's as long as this potential is quadratic.
Okay, but your picture is nearest neighbor.
No, because I also had this chain which is
okay,
connecting
okay,
this guy to here. Right?
I see.
So as long as this is quadratic, that's fine.
I see. So,
okay.
Okay, thank you.
So basically, as long as this is quadratic, so your Lanzhou equation is linear. So that's the important thing. Okay. So you have a basically linear Lanzhou equation, and this linear Lanzhou equation immediately tells you that xv, this phase space variable, is basically a Gaussian distributed. Okay. But this heat, so heat in this case, I'm just defining that the heat coming from this bath to this particle. So this is how the heat is entering the system. So I'm looking at the heat entering the system from the left bath. Okay. So this is, you can think of it like a force by this bath, because this is the fluctuating force by the bath, and this is the dissipative force. This is like the net force times this velocity, and when you integrate it, it's like the work done by the bath on the system. So this is the heat. Okay. So what I want to draw your attention is that we have a linear Lanzhou equation and you have a quadratic functional. Okay. So, and you are interested in the distribution of these quantities, and in particular, basically you are interested in at large time behavior. So basically you are interested in this large deviation form. Or equivalently, basically you are interested in this generating function, which has this form in terms of this tau, exponential tau mu lambda, and possibly there is a prefactor, and you are interested into finding this mu of lambda and this prefactor. Okay. So formally, so the way you can do this is basically, okay, so you can find out the general joint distribution of this heat and this phase space variable. You just shorthand for x and v. So this joint distribution, and you weight it with exponential of minus lambda q. So when you integrate over all q, so that's the generating function. So it satisfies some kind of partial differential equation. So this operator, this differential operator, this is just the normal Liouvillean term, which just coming from the Hamilton dynamics. So this, what you see is the Liouvillean in the phase space density. And this is the term basically which says how this coming from the interaction with the left bath, and this term is coming from the interaction with the right bath. And this term with where lambda appears, this corresponding to the fact that, okay, you are also looking at this q variable, or basically in terms of, in the lambda space. Okay, so this is the term coming. So if you put lambda equal to 0, this term disappears. So as you see that if you put lambda equal to 0, you are just integrating over q. So this is just the phase space distribution, the distribution of u. So if you put lambda equal to 0 here, this z just basically the phase space probability distribution. So this L at lambda equal to 0 is just a normal Fokker-Planck operator. Okay.
So, so this QL is like the energy of the left bath. Is that the thing? Or?
So QL is the energy coming from the left bath to the system in a given amount of time.
Is the energy flux? I see. So
energy to the net energy flow.
Yeah. Can you just go back to the previous slide just to see this expression for QL once more?
Yes.
Okay, so yeah, can you explain how you get this? So what is this?
This object, right?
Yeah.
Okay. So so let me give you a short answer here, and then I'll give you a long answer end of the talk. The short answer, you can just think of it is like that. So this eta L is the Gaussian noise coming from this bath. Basically, all this water molecule is hitting this particle here.
Right.
So this is basically the force applied by the bath. Minus this is like a dissipative term, this Stokes dissipative term. So this is like the net amount of force applied by the bath to the system, to this particle.
Okay.
And you multiply with the velocity, that's like the power injected, net power injected, and you integrate, that's like a work done by the bath.
Okay, right.
And that you call it heat. But okay, maybe at the end of the talk, I'll just also give you another way of looking at this thing. So there, I think it will become more evident actually that this is the heat, actually.
Okay, thank you.
So just remind me at the end of the talk if in case I forget to just tell about this again.
Okay, thank you.
Okay. So now this object now, okay, so this is your operator. This is your differential operator, as I told. And now, just like this Schrodinger equation, so this operator, you can basically expand this in the eigenbasis of this operator. Okay. So it has this discrete eigenvalues, mu n, and these are the corresponding right and left eigenvectors. So unlike the Schrodinger equation where this operator H Hamiltonian is basically Hermitian, so which case basically your left eigenvector is just a complex conjugate of the right eigenvector. So in this case, this is not just a complex conjugate of this right eigenvector, but otherwise it's like a similar distinct. So you have this operator, differential operator, and you basically find out its eigenspectrum and corresponding eigenvalues, left and right eigenvalues, and you can expand there. And at large time, yes.
And Sanjib, your summation goes up to infinity. Does that mean that you are looking at infinite system already? So the summation in the value.
So what I mean is that it basically whatever n it covers. So in other case, you just take this guy to be 0 basically. So it's whatever full eigenspectrum is you are just writing in. You're
just summing over. Okay, but for a finite system, there will be finite. Okay.
Yeah, exactly. So in that case, basically, you just put all these other guys to be 0.
I see. And
there are finite number now.
Yeah. And you are assuming that there is a gap. Yeah.
So I'm assuming that there is a gap, and I'm also assuming that this spectrum is discrete basically.
Okay.
So this is something I'm assuming without proof, basically.
Okay.
So if this is the case, so if this is the case, then at large time, so what you see is that basically this term will be dominated by the largest eigenvalue, which I just call it mu lambda, and the corresponding eigenvectors, left and right eigenvectors. And these are the subleading terms, basically. And given this, you can find out the generating function, basically just by integrating over this final variable, phase space variable, and also average over this initial phase space variable with respect to the steady state. Because I want to find out this heat flow in the steady state. And steady state, as you know, that you can find easily because I said that when we put lambda equal to 0, that corresponds to the usual Fokker-Planck equation. So therefore, steady state is just if you put lambda equal to 0 and tau goes to infinity, that gives you the steady state. And you know that if you have a system which is a steady state, so then mu at lambda equal to 0 should be equal to 0. So this guy goes away from there. And this guy should be equal to 1 at lambda equal to 0 because steady state cannot depend on the initial condition. And so therefore, this object at lambda equal to 0 is your steady state distribution. So given that, you can just also find out g of lambda. Of course, this is very formal, but...
sorry to interrupt. So your L lambda is not to the Fokker-Planck Hamiltonian, right? I mean,
it is not the usual Fokker-Planck operator. When you put lambda equal to 0, that's the your usual Fokker-Planck operator.
When I put lambda equal to 0, I see. That
0. So when this term, because when you put lambda equal to 0, you are integrating over Q. So then you are basically looking at the phase space distribution. That's your usual Fokker-Planck operator.
Yeah, there I usually look at the marginal distribution after integrating out the noise part. I mean the eta. Now you're integrating out the Q. So that is what is confusing me a little bit.
Okay. No. Okay. So, okay, maybe I understood what you're confused. See, this is a Landsberg equation, which is a differential, stochastic differential equation.
Yeah.
Right? So their noise is there. So corresponding to this Landsberg equation, you can write down this Fokker. So let's call this also Fokker-Planck equation, basically. So corresponding to this Landsberg equation plus this definition of heat, so you can write down a equation for the probabilities. So let's call it Fokker-Planck equation, okay, to avoid this
kind of Fokker-Planck equation, not
kind of Fokker.
Okay.
Yeah, exactly. Yeah. And this Fokker-Planck equation, there is no noise there. This is a deterministic equation. It says how the probabilities evolve, basically. Okay. So now, actually the upper equation for P, Q, U would have been the Fokker-Planck equation, but now this is a upper equation I'm just getting from the Fokker-Planck equation of this probability distribution basically. So there is no noise in this equation basically. So this is the equation how it says how the probability distribution evolved basically.
Meaning that you are fixing the noise term, or
no, I'm not fixing. See, so given this X, M, and Q, so I could have written down a Fokker-Planck equation which says that okay,
so your noise has gone inside the QL.
Yeah. So this one is some other L, not call it. Let's call it some. Okay, let's not call this L, but let's call it a straight L, and P, which is a QL U tau given U0. So this is a Fokker-Planck equation, where you can also find this operator L, where the now variables are Q and U. So now if you multiply this equation by exponential of minus lambda Q,
right,
and integrate over Q, so this is the equation you will get basically.
Yeah.
So there is no noise in that sense because there is no noise in that equation. So this is the equation which says how this joint probability distribution evolved in time.
But
so
in a way, your noise has gone into, it's been subsumed by your QL. And
so the noise has gone into deriving this equation basically.
Okay. All right. Got it.
Okay.
Got
Yeah.
it. And
So
this L operator you say is not self-adjoint, huh? The way
this is not self-adjoint. The way it's not Deiger. L Deiger is not equal to L basically.
So normally the asymptotic state would have been given by the zero mode of the Fokker-Planck operator. Now
So
it is like the right-sided zero mode versus, I see. You have two sets.
Yeah.
Okay.
Yeah. But the eigenvalue is the same. So it's the same energy.
The eigenvalue is okay. So again, zero eigenvalue would give the asymptotic state, and the subleading guys would give you the approach to the asymptotic.
Yeah.
Okay.
So in some sense, basically, you have these two eigenvectors, let's say psi and chi. Right. So when L operates on psi, which gives you mu psi, and where L operates on chi, which gives you again mu lambda times psi with chi.
I see.
So it operates on the other way. Okay, so you can just think of it like chi L is like a chi mu lambda.
Okay.
Something like that. Yeah. Okay. Yeah. Okay. So it's just that these are not just a complex conjugate, but otherwise it's like this your Schrodinger equation basically. Like.
Yeah. No, thank you.
And this is like a okay.
Right.
So this is like the same Schrodinger decomposition basically in the eigenbasis. Of course, what I have told you is just a formal listing, but we don't know how to solve this Fokker-Planck equation because it's like a very complicated Fokker-Planck equation.
Yes.
So nevertheless, so what is this with Anupam and Abhishek, what we have found out is that given that this is Landsberg equations are linear, and you are looking at the quadratic functional, so you can actually find out your mu lambda and g lambda exactly. So what you can do basically in terms of looking Q in the time domain, so you can look at in the frequency domain.
Okay.
So basically you just look at the heat flowing in each frequency channels. And it turns out that the heat flow along each frequency channels they are independent of each other. So therefore you can actually find this expectation value independently for each channels, and these are still quadratic functional of the noise. So therefore you can actually find it exactly. And in particular, when you take t going to infinity, basically large t limit, it should be tau actually. Okay. Then the dominant term is basically given by that. Okay. So in the sense that you can actually find what is chi and what is psi and what is chi corresponding to this mu of lambda, and then you can find g of lambda. And these are exact basically. So what we have found is that we do not know how to solve this Fokker-Planck equation. Nevertheless, we can find the lowest or highest eigenvalue, whichever way you call it, basically largest eigenvalue, and the corresponding eigenvectors exactly. So the eigenvalue is given by this. Okay, so this is exact, and you note that okay, this particular thing lambda appears only here, and which basically implies that your mu lambda has basically this kind of symmetry. And this symmetry also implies that your large Davis. Sorry.
This is an implicit equation. Yeah.
This is yeah. You just need to. This is basically given this and this z. You can actually go ahead and in principle solve it. In principle, if you provided that you can do this integral. It's just a matter of doing the integral.
Okay. Where is the information about your harmonic frequencies? I mean the eigenvalues of the phi. Oh, here it is. Right here. In your
this inverse matrix.
Okay.
Yeah.
Got it. Yeah. Thank you.
And this mu is known as the Galois coherence symmetry. And given this symmetry, so your large division function satisfies this symmetry, provided g of lambda is analytic, as I said. Okay, because if g of lambda is analytic, then this h is related to mu by this Legendre transform. Okay, and this is basically the fluctuation theorem or large division symmetry. But this is given the provided g of lambda is analytic, so we need to also find what is g of lambda, and we can also find what is g of lambda exactly. Okay, it's pretty complicated, but okay, we have an exact expression for g of lambda.
So Sanjib,
so now you want to, yes.
So the symmetry, the Galois coherence, could you relate to any symmetry of the L operator? Is it?
You can, but I think here it was, I think what I remember is that it was not very clear because see, this is your L operator, right? And
yes.
Lambda appears only here. So it was not very clear, but it's possible that you do some kind of transformation and then you go some L prime of lambda where that L prime of lambda might have that symmetry actually.
Right, I'm asking because for the exclusion process, you can show that it is related to a invariance and the similarity transformation of this L operator.
So in some cases, basically what you can do is that this L lambda, so you can actually go to a Hamiltonian picture, and that Hamiltonian has that symmetry.
Okay.
So in simple examples, you can actually find, but okay, here, okay, it was not evident to us basically. Okay. But in simple cases, you can actually show that this symmetry is related to the. So you can go from this picture to a Schrodinger equation where there is a Hamiltonian corresponding to this L, and that Hamiltonian has that symmetry basically.
I see. Okay. Thanks.
Okay. So you can also find this g of lambda, but okay, it's pretty complicated, but you have an exact form. So then, okay, we just wanted to look at some special cases because, okay, whether this is true, first you want to find out this formalism, whether it's correct or not. So you look at it, suppose you have just one particle and then connect it to heat bath, okay? So again, you want to find out how much heat flows from this thing to this particle in a given amount of time system. So you can again find out mu of lambda and g of lambda exactly. And this is a problem which was actually solved earlier. And in this case, actually, you can solve this Fokker-Planck operator exactly. And in that case, basically, L lambda, you can just go to it basically becomes a Schrodinger equation of a harmonic oscillator. And your H of lambda has that symmetry. Okay. And okay, so this is a verification that, okay, this formalism is correct. So this is another case, okay, I looked at this where you also have a potential, confining potential. So in this case, also you want to look at heat flow. Okay, so mu lambda is given by the same, but in this case, z lambda turns out to be different. So independent of k, however, it's not same as k going to zero limit. It's just the square of this k going to zero limit basically. K going to zero and k equal to zero, these two are different basically in this case. Okay. In this case also we have found, and in this case it turns out that depending on the parameter range, actually this g of lambda can have singularities, and when this g of lambda has singularities, then in those regimes basically your heat distribution of the heat doesn't satisfy this fluctuation theorem. Okay, but okay, let's forget about the heat. I just want to talk about an experiment. So this is an experiment done in Celebators group. So what they looked at is, this is a AFM cantilever. So this is okay, very small size. And this is a conducting plate. So you just keep it near the cantilever. So this is a metallic cantilever. So now, so you apply a voltage between this cantilever and this conducting plate. And then once you apply voltage, this basically behaves like a capacitor. So therefore, there is a force on this cantilever, basically. This is a fixed plate. So now if you basically apply a random voltage here, so that applies a random force on this cantilever. And what they wanted to find out, what is the work done on this cantilever by this external random force. And this is the way they define. So basically you look at the tip of this cantilever and you just multiply the force with this velocity of the tip, and then you integrate over time. So that's the net work done in a given amount of time tau. So you make it dimensionless. Okay. So alpha is some parameter. Okay, is basically the proportional to the strength of this force with respect to the thermal bath. So I didn't tell you. So it's in the air. So air basically acts as a thermal bath. So it's in air. So air thermalizes this cantilever, and on top of that, you are basically applying this random force. And then they looked at this distribution of this work by this thing, and then they plotted this distribution for various values of alpha. And they also looked at this fluctuation theorem, which is basically, okay, you look at this ratio in log. So if fluctuation theorem is satisfied, so it should be something like that. So in terms of this dimensionless, this thing, so which is basically this quantity, so you call it small w. So if fluctuation theorem satisfied, this should be linear. So this is what they have found. But they have also found where it's basically deviates from this linear line. So in some parameter range, it doesn't satisfy. So it turns out that actually you can model this system by a harmonic oscillator in a bath, which is in that case basically air is providing the bath. And on top of that, there is an external random force. And we are interested in finding out the work done by this external random force. So this one, we can actually compute the generating function of the work done. So which is, as I said, it should be given by this. So where mu lambda is given by this, so it has 2 branch points. But okay, these branch points, okay, they do not affect much. But this z lambda, so it also has a pole if your parameter alpha, which basically says that how far this system is away from equilibrium. For large alpha, it has some kind of pole. So if near the equilibrium, basically this z of lambda is analytic, but far away from equilibrium, it has some kind of pole. So as this, to answer this deep question, so without solving this, there is no way to know that, okay, why is this 1/3, or okay, why is this, I mean, you know that, okay, if you're going away from equilibrium, there is some kind of this thing, and near the equilibrium, it's fine. But apart from that, okay, you cannot say much. And corresponding to this, you can also find out the large deviation function. For less than 1/3, it's just given by the normal saddle point. So where h1 is given by this is just a saddle point calculation. But for alpha greater than 1/3, so there is a critical value of W star, which is given by this. And beyond W star, it's still given by the saddle point, where your large deviation function is given by that. But when W is less than W star, your large deviation function is different, which is given by this. And this large deviation function undergoes a second order discontinuity at W equal to W star. And as it turns out that this second order discontinuity is quite generic whenever you have a singularity in this prefactor z of lambda. Okay. So, okay, you also want to compare it to experiment. Okay, so if you want to compare it to experiment, usually you also need this subleading terms because, okay, otherwise you have to go to very large time. And you can also actually find out this subleading term explicitly for both alpha less than 1/3 and alpha greater than 1/3. So let me stress you this point that these expressions are exact up to this order. So there's no approximation involved. So this plus the lower order term basically. So these are exact expression up to this order. And you see that, okay, if you compare with simulation, it actually matches pretty well up to 10 to the minus 10. Okay, and this is for alpha equal to 1/3, and this is the case where you have a critical point. So as I said, that this is an experiment, and okay, of course you want to compare the experiment, and as you see that, okay, it matches extremely well with the experiment. Okay. So this is okay. So there is also another experiment where, okay, there is this particle where colloidal particle, so it was trapped in a harmonic trap, and then you just keep moving the trap in some random fashion. So, okay, so there's a correlation in the trap position. And again, you want to find out, okay, how much is the work done by this trap. So again, okay, so they looked at this work done for various values of alpha, and there's also this parameter delta, which basically gives the ratio between these two time scales. So one is the time scale of this trap modulation, and the other is the time scale of the this trap strength. So given a harmonic trap, this particle relaxes, and that's the relaxation time. So now, okay, so there also they have found that, okay, there's a fluctuation theorem is satisfied in some region, and in some parameter region it's not satisfied.
So Sanjib,
and again,
the temperature is the temperature of what here? The temperature of the colloidal solution.
In this case, the temperature is the temperature of the bath. It's just in water, basically. So temperature of water.
And in the previous one, the temperature was
previous case,
temperature of air.
Temperature of air. Yeah, exactly. Yeah.
Okay.
Yeah.
And Sanjib, this singularity that's coming from the G, is it somehow you could relate to the gap between the largest and the next largest eigenvalue going to zero?
No.
That's how you
no.
No? In this case, you can.
No, because you see that, no. Because in all cases, you cannot, because you said this G of lambda is just coming from the integrating this eigenvectors corresponding to the largest eigenvalue.
Right.
Right, because I did not even looked at the other eigenvalues and their terms.
Right.
So it just, so therefore it's just coming from the
but you're saying that even
terms corresponding to the,
yeah. Yes, at this point, you have also could see that the gap also remains non-zero, and it's purely coming from the prefactor.
Yeah. So I do not know now to answer your question. So you are asking, suppose there is a system where the gap vanishes, and what would happen there? So I do not know in that cases. So these cases, basically, I'm assuming that there is a gap.
Yes, okay? Because the transitions in the interacting particle system. So, for example, you take WASP or things on a ring. There is a transition that happens when the gap vanishes, as if I understand. And so there probably is a different origin, but yours is different origin. Okay, I understand.
Okay, yeah. So I do not know. It's possible that at that parameter range, even the gap also vanishes, and that one can actually check. I mean, like for example, in the single particle example where you have the exact, exact solution. So one can check, but I do not know. But I think. But I think probably it's not the case, but I cannot tell you exactly. Maybe it's worth to look at it actually.
Okay, thanks.
I mean, in this case, in the case where you can actually have a full solution.
I see. Okay. Yeah, thanks.
Okay. So in this case also, so we can actually model this system. I mean, this is a Brownian particle in a harmonic trap about x0, and this is just a thermal noise coming from the bath. And as I said, the position of the bath also actually keeps moving. And in this case, basically it just moves by a Ornstein-Uhlenbeck process. And you are interested in this work. So again, you can find out the generating function, and corresponding mu lambda and z lambda, you can find it explicitly. Okay. So again, mu lambda has these two branch points, but that doesn't affect much. But this z lambda is, in this case, turns out to be much more complicated. And in this case, in there, we have just one pole, but here, depending on this parameter regime, you can have one singular, no singularity, or one singularity, three singularities, or four singularities. And corresponding to this parameter regime, you can actually find out this large division function exactly within its state. You can also find out actually not the large division function, but the full probability distribution function, to the lowest order exactly. And if you can, this is a comparison with the simulation basically, and you see that that matches quite well. Okay, so the main message of this is that basically so in stochastic systems where your state space is infinite, so even with short range correlations, you can have singularities in this prefactor for this generating function of this additive observable, and this singularities actually alters this large deviation function, and when it alters, basically it alters with a generic second order discontinuity. Okay, and so this is basically the main message of this talk. So now I want to just talk about another second part of this talk is basically, okay, so I want to talk about something slightly different. So I want to talk about the symmetry properties of this entropy production. Okay, so imagine that, okay, so you have this bath. So bath degrees of freedom is always this fast degrees of freedom. So you just model the bath by this noise. So, okay, so you don't take into account this bath degrees of freedom. So when you talk about the degrees of freedom, these are the slow degrees of freedom. For example, the position of this Brownian particle or the velocity of the Brownian particle. Okay, so you have some system consisting of these slow degrees of freedom, and you want to find out the entropy production. So let's say this system is driven out of equilibrium, or this is in a non-equilibrium steady state, and you want to find out the entropy production of this system. It's possible that there is another system, again slow degrees of consisting of slow degrees of freedom, and it's connected to this system you are interested in, but you may not be aware of. Okay, so now you are interested in the entropy production of this one. How does the coupling to this outside system affect the entropy production of this system? Okay, you may not know that there is something there. Okay, does it affect, or how does it affect it? So before that, I have to tell you what is the entropy production. Okay, this is the term you have already seen. Basically, this is if Q amount of heat basically coming from the bath to the system, then minus Q by T is that's the entropy production in the medium. Plus, you can also define an entropy production in the system. So this is basically the Gibbs entropy, basically minus P log P is, if you just assume that it's like an average entropy, then log P is like a entropy. So it's just the difference between this log P's at two different times. And here P refers to the probability density, probability distribution of this phase space variable basically at time 0 and T. Okay, and where these are the distribution. So these P's are some functions, so they evolve by Fokker-Planck operator, so you have a functional form for P. So if you are interested in the steady state, so this both P0 and PT, they are same. So these are just a steady state distribution. So P is a deterministic function, but the U inside this P or U0, these are random variable. This is the variable at that time. Okay, so therefore this is also a stochastic quantity. And so that together, this basically defines this entropy production. And given this definition of entropy production, it's very easy to show that it satisfies this fluctuation theorem exactly at any time. You can also write down a large deviation formulation of this one. So it says that, okay, you just look at the divided by the time. So the small s has this large deviation form. So corresponding to this, basically this I of s satisfies this symmetry. So this one is basically says that how much this asymmetric this two probability distribution are. So sometimes you refer to this as the asymmetry function. Okay. So now let me just give the statement of the problem. So suppose I have a system A, which is coupled to some system B by some coupling. Of course, if you take A and B both as a whole system, it's your full system. And if you compute the entropy production, then the distribution of this entropy production will satisfy the fluctuation theorem. Okay. But if this delta is very large and you are just considering only system A, you are ignoring B, there's no reason to believe that, okay, the compute the entropy only taking into account this A will satisfy fluctuation theorem. Okay, but if delta equal to 0, of course they behave like a two different system. This is an isolated system. It will again satisfy fluctuation theorem for both A and B if this delta is equal to 0. The question we wanted to ask is, okay, is there any deviation from fluctuation theorem when you take delta going to 0 limit? Okay, so delta is small, very small, and in that limit, can you see any signature of this coupling? So let me just give you the answer. So what we find is under certain driving protocols, so there can be significant violation of fluctuation theorem. Basically, you will see that violation, deviation from fluctuation theorem, even in the limit delta going to 0. So in that case, basically this delta going to 0 is a singular perturbation. It's not a regular perturbation. And deviation might mean deviation might just mean either it's, okay, it might be even linear, but with a different alpha not equal to 1, or it can be something else. Yeah, there's a question.
Yeah, Sanjib, so when you're defining now this entry production, you're defining over a certain time as well. So how do you scale the time with respect to delta?
Yeah, so that's what I'll come actually. Yeah.
Okay.
Yeah. Okay. So now, so assume that this your mu of lambda. So let me just remind you this thing. Okay, you are looking at the generating function of this delta S. So there's a mu of lambda corresponding to this. And okay, there's a g of lambda here, but in this case, it turns out that it's not important. So I'm not going to focus on that. And given this mu of lambda, so okay, this S is just the scale, this thing. So it has this large deviation form. So where I of S is just related to mu of lambda by this Legendre transform, basically by this saddle point equation. Okay. Now suppose that your mu of lambda has branch point singularities. Okay, this is analytic within some region, and there is a branch point singularities outside this. Okay. So when you compute by this way, so basically when you compute in terms of I, so you have already assumed that you have taken time going to infinity. Okay. So now, so given this, so what you find is that, okay, so your lambda star, if you have a system like that, you have branch point singularities of mu lambda, and it's analytic within this, the saddle point remains always within this analytic region of mu of lambda. So what happens is that when S goes to minus infinity, this saddle point goes to one of the branch point, and then as you increase this thing, so saddle point changes, and it, at the other limit, it goes to the other branch point. So therefore, this saddle point at these two limit basically converges to these two branch point. Okay. So given this, you can write down this I of S. So this is this mu of lambda at that branch point plus this term. This lambda star is just the lambda that branch point plus S plus this higher order term. So then you immediately can see this, okay, I of S and I of minus S is just, okay, this is the difference between this mu, and this one is just a difference between these two, but because you are looking at minus S, so that becomes plus, and then there is higher order term. So there is no reason.
Sanjeev, are these like square root branch points, or
there are square root branch point, but it can be need not be square root branch point. It can be branch point of some power, basically, something to the power p, which is let's say less than 1. Yeah. So it need not be square. It need not be square root. Okay. So and then you have this higher order terms. Okay. So this guy need not be equal to 0, which you need for the fluctuation theorem to be satisfied, and this need not be equal to 1. So what happens is that if you put delta equal to 0, so where you know that fluctuation theorem is satisfied, in this case, because of this Galaxy symmetry, in that case, this 0 corresponds to delta equal to 0. So this branch point, they also, this saddle point, they also satisfy some kind of symmetry as a consequence of this Galaxy symmetry that you can see basically easily by taking this expression and just differentiating and from there. Okay. So therefore, when you take S going to infinity, that corresponds to this symmetry basically, because the saddle point just becomes this branch point. This is the case delta equal to 0, where the branch points are lambda plus and lambda minus. So that becomes 1. And as it turns out that this higher order term becomes 0 for this case, because this, you know that it must satisfy that. Okay. But for general lambda, this need not be the case. And this I'm just trying to show it here. So this is the case delta equal to 0. And this is some case general delta, and it has some eventual slope. It's given by these two branch points. So the question is basically what happens when you take delta going to 0? Whether they just go back, this red line becomes this dashed line, or it remains something different. Okay. So even without doing the calculation, okay, there are some 4 possibilities. Okay, whether you do not know these possibilities are actually existed or not, but there are at least 4 possibilities. They both this branch point go back to the original branch point. So this lambda plus minus delta just becomes lambda plus minus, or one or both of them become something else. This the lambda plus minus till this. So if this is the case, basically then that is a case of a singular perturbation. This slope basically doesn't become the same as that slope. And if this is the case, this becomes regular perturbation. Okay. So, but this is, I'm just saying that this can happen, but I still have to show you that this happens, right? I have not shown you. And okay, I'll maybe show you the general case later, but okay, so what we found is that, so we can actually one setup where you can take these two Brownian particles coupled by a harmonic spring, and then you put these two random force on these two particles, Fa and Fb, to drive the system out of equilibrium. And you take this k going to 0 limit, I mean, k in the sense that you take delta, basically you just make it a dimension-less coupling. And you just look at the entropy production due to the system A. Okay, you can define this entropy production certain way, but let me not go to detail. So, and then you see that, okay, you can actually realize all these four regimes, possibilities, P1, P2, P3, P4, right? So you can find basically cases where your fluctuation theorem is not satisfied, and this is what I wanted to show. So this is the case where fluctuation theorem is satisfied, but in these other cases, basically fluctuation theorem is not satisfied. Okay, so you can actually understand this. I mean, just by analyzing this saddle points, but let me just not go into the detail here. Okay, or I can go into the details after the talk if you want. Okay, so but okay, now if you put this system in a harmonic trap, what you see is that actually this lambda plus minus delta always go back to lambda plus minus in the limit delta going to 0. So as soon as you introduce a harmonic trap, you confine this system. So your influence of this other hidden degrees of freedom goes away. Okay, so basically trap, you can, if you suspect that okay, your system might be coupled to some other thing, you can just put a trap, and that nullifies your coupling to other degrees of freedom. Okay, so you can also do this in other system. For example, this here you can look at this heat conduction through this particle, and then you couple to other heat bath through some weak coupling. Again, you see that okay, your fluctuation theorem is satisfied, violated even in the limit delta going to 0. Again, you can understand this by analyzing this whatever branch point singularities. Okay, so to understand this, to just summarize this part. So basically, what we have seen that we have found a mechanism by which fluctuation theorem of entropy production can be violated in the presence of a coupling to a external system, even in the limit when coupling state goes to 0. Okay, and basically by looking at the system at large time, because since we are looking at this in the large deviation form, so where you always assume that your time is very large. So basically, if you look at the time scale, which is inversely proportional to the coupling strength or something, you basically this coupling shows up, and then if you just put a confinement, that whatever this weak coupling, it becomes a regular perturbation. Basically, it doesn't affect the this thing. So we can also see that okay, as I said, that this coupling to the external systems are coupling to slow degrees of freedom. But you can also check, basically you can couple to another heat bath, which is a fast degree of freedom. You can weakly couple. And in that case, weak coupling doesn't change the fluctuation theorem as you expect, because the coupling to basically unaccounted fast degrees of freedom doesn't affect the fluctuation theorem. Okay. So how much time do I have? Can I just take 5 or 10 minutes so that I can just go to the last part?
We are almost out of time, so yeah, I think if you can just wrap it up.
Yeah, so I'll probably just take 5 minutes and I'll be done, probably.
Sure,
yeah,
okay.
Okay. So let me just talk about this briefly. This fluctuation of this ratio observables, which is basically the ratio of two extensive quantities, which are these are each of these quantities basically they follow large deviation principle, and you are looking at this ratio basically. Okay. So is there a large deviation form for this kind of quantities? For example, you can look at this. So what I mean is that a P of W and W2, they follow some kind of large deviation principle, and you are looking at this ratio. Okay. So given this P of W and W2, of course, you can write down P of eta in terms of this joint distribution. And the question is whether it has this kind of form. So it's not a priori evident that it will follow a this kind of form, because if suppose you take W1, W2 is just some kind of Gaussian with mean 0, so you can of course find out the distribution of eta exactly, and it's just a Cauchy distribution. Of course, it doesn't have a large deviation form. On the other hand, suppose you take W2 to be just time, so then you know that it's basically eta is just W1 by the time, and you know that it has a large deviation form. Okay, so basically joint distribution is something like that. And of course, delta function is, you can write it as some limiting form of some other function. So that says that, okay, I mean, there might be a large deviation form. And this is basically, these people have found is that, okay, so if we can take a general Gaussian distribution, and in that case, actually, you look at this observable, minus W1 by W2. Okay, this sign doesn't matter, but it's just a convention. So you see that it has this form where eta follows something like that, J of eta. So you see that it has some form, and then it becomes a constant. And as you see that when this guy becomes constant, I mean, this no longer, it doesn't determine anything, because if something this become constant, if I don't give something, probability distribution becoming constant doesn't mean anything, because it has to be normalized. Okay, so then this prefactor, I mean, takes over, and generically you can show that basically this prefactor has a 1 by eta square form for large eta. So it has this power law for large eta, and in between it has this form. So we also wanted to look at this problem, because that was a very simple problem, and then we said, okay, how does this singularities in this large deviation function affect this kind of entropy production, distribution of entropy production? And we just looked at a simple example where we have just one particle in water. So it's like a particle in a heat bath. So there are these two external forces. They are acting on this particle. They can be either independent or they can be correlated. So you can look at both cases. So accordingly, you can define two work corresponding to each force. And then you can just look at the ratio of this. Okay, you can just, I mean, don't pay too much attention to this thing, because this is, okay, just you can just think of it as one is like the output work and one is like the input work, and that's why this minus sign. But it's basically, you are just looking at a ratio of two extensive observable. And in this case, actually, you can again find out this G of lambda and mu of lambda exactly. I mean, G of lambda turns out to be actually quite complicated in this case, but okay, because it's also in the lambda 1, lambda 2 plane. And okay, so this is the, you can find out this generating function. You can actually find out the large deviation function of this both joint large deviation function by this, which is given by this, where this is there. You can also find out this thing. So this is the case where this guy doesn't have any singularities in this region. Okay, so where you can find out this large deviation form exactly, and which is this, and then okay, you can also find this p factor, which is 1 by eta square. I mean, this is not surprising, because okay, this is, I mean, this is quite generic. It should be 1 by eta square. And okay, this is the probability distribution function. Okay, so this problem is actually, well, it was a bit complicated, and so okay, so we just looked at this case where there is no singularities, and the case regimes where there are singularities, we just evaluated this numerically. But recently, Supriya actually and collaborators actually, they have actually looked at this problem, and again, there's another problem there, and they have actually found very interesting result. And what they have found is that so this is the problem, this is our problem basically, and where they have found is actually this singularities actually contribute to a kink in the large deviation function corresponding to this efficiency fluctuations actually, yeah. And that's actually quite nice result actually, yeah. Yeah, and this is some other system, and okay, here even large deviation function shows very, I mean, strange, but I mean, when you find this strange, it's quite nice actually, properties actually. And okay, so to conclude the talk, basically, okay, I have talked about 3 aspects of large deviation in non-equilibrium systems, and basically fluctuation in the context of fluctuation of additive observables, and talked about second order discontinuity large deviation function coming from a singularity in this prefactor of this generating function. I have talked about this hidden degrees of freedom and corresponding the symmetry properties of this large deviation function of the entropy production. And I have also briefly talked about this ratio of time additive observables, basically. Yeah. Okay, these observables. Yeah. Okay. Yeah. Thank you very much. And okay, if there's any questions, I'd be happy to say. And okay, I'll be happy to also go through some of the details. I think there's something about the heat or something. Okay. Yeah. Yeah. Thank you very much.
Thank you, Sanjib.
Yeah.
For a very nice talk. So I think I have 2 more questions.
Yeah.
Yes, Sanjib, so I had one question. So you have this, let's say the work of also the last work that you showed with the singularities in the large deviations, or also before. In certain examples, such singularities could be associated to dynamical phase transitions. So it's like you are looking at different regimes of these parts in the large deviations. And they correspond because there are different optimal paths or something like this least action paths that corresponds for the 2 different regimes. Do you see these kind of things in your systems as well?
Okay. So we did not actually look at the path, but I think intuitively what we understand is that, see, always this singularity appears when you go far away from this equilibrium. So where you have more fluctuations. So somehow basically this, and see this, this prefactor is coming from this, your, the eigenvectors in the initial corresponding the initial and the final condition when you average over. So therefore, I think it's basically when you are into this far away from equilibrium, there are this large fluctuation in the either in the initial condition and the final condition. So I think those are the path. I think either start with very far away from this your equilibrium or typical trajectories, or ended up in basically your typical trajectories. So I think if you just look at in the trajectories, you will probably see that those are the trajectories which are probably contributing to these singularities. Yeah, but we did not, I mean, we have not looked at this in terms of the trajectories, actually, yeah.
Okay.
So this is just a guess, yeah.
I see. And just on this, if I could ask the second question, that yeah. So I understand from your analysis how the Galois-Cohen kind of symmetries are breaking down. But could you say something about like what are the properties in the underlying dynamics? By looking at it, I could say whether the symmetry would be valid or not. Is there some understanding? Like what do I see?
See all this yeah. See, I think see all these examples. What we looked at is either the heat flow or this external driving, whether these drivings are stochastic, right? Either the heat flow, it's just a stochastic force by the bath, and this external force is a stochastic driving. So where you have, when you have this stochastic driving, you don't have this control over the force you are applying. So I think whenever you have this kind of random force, you can see these violations. But on the other hand, if I put a deterministic force, my force always remain within some given, I mean, the force is always well behaved, so that probably the system doesn't go very far away from the equilibrium, I guess. And so probably in that case, probably it doesn't violate this symmetry. But on the other hand, if my driving is either, I mean, whenever you have a stochastic driving, you have a possibility of violation of this Galois-Cohen symmetry. So, but the eigenvalue doesn't break the Galois-Cohen symmetry, only the eigenvectors which break the Galois-Cohen symmetry.
Sorry, it's noise coming from Piyush, I think. Oh, sorry. Yeah. Okay. Thanks.
So I had a question.
Oh, sorry, Deepak, you had a question. I'll go after you.
Okay, after you.
Oh, thank you. Thank you, Sanjib.
Yeah.
Actually, Yeah, I had a question about those. If you had a finite state space, maybe you will not see those kind of.
You'll not see those things because again, so as I said that when you have a random driving, so what happened in the infinite state space, basically you can throw you can throw the system in a very far end. You can have very large velocities, for example, which contribute to a large amount of heat or whatever work done in the system. But if you have a finite state space, then you will not have this kind of singularities, and you will not have violation of this fluctuation theorem. So this appears when you have basically a infinite state space.
So
I think you need infinite states.
Yes.
I think you need infinite state space, and you need also this kind of some kind of random driving on which you do not have control over, basically. Like, for example, if I put a deterministic force, I mean, okay, system will behave some way, but I think it will not throw the system very far away to have very large velocities or to have large positions, for example.
Also, I think you would not have seen a violation of the fluctuation theorem if you had taken the full entropy
so that's what I'm saying. So if in the case, if you take full entropy production, you'll never see violation of fluctuation theorem because that's like a theorem.
Exactly.
Right? But exactly. So you never have a fluctuation of entropy production doesn't show any violation of fluctuation theorem.
Yes.
But the point is that sometimes the other quantities which is similar to entropy production,
yes,
or you look at the entropy production of a partial system which, okay, you have neglected some degrees of freedom. So in that case, basically, you might see this violation of fluctuation theorem.
Right. Yeah. Thank you.
Because because for the full entropy production, it's just a theorem and it's just a actually very trivial proof, right? Like 3-line proof or something.
You've almost
so
constructed it in a way. You've almost constructed it in a way.
You almost construct in a way so that you will never have this violation. Yeah.
Exactly.
So that's why that's also not very interesting, in the sense that, okay, I mean that's some theorem, but okay. It's there, but okay.
Yeah, sure.
Yeah. Yeah, Deepak.
Yeah, so my question was sort of much more. So you said that if you have a confining potential, then the violation is not seen. If you have a weak coupling of between system A and B, then you put them in a confining potential. But if you put them in a confining potential, then they are more likely to interact with each other. No? The interactions become stronger when people are close by.
But you can have a weak confinement also.
Yeah. Yes, So naively that if you confine them, then you will see bigger interaction between them, and hence more likely more violations.
But what happened? The interaction is very small. So what happened actually? Okay, so let's see. Why do you see this violation of the fluctuation theorem when you don't have confinement? I mean, it's a physical listing, but it's mathematically it's not always the case that okay it works. But one physical understanding is that okay, if you have a weak coupling, so initially they behave like an independent particle. Just think of it like a two Brownian particle connected to it by some harmonic potential. But over time they will go far away. As they go far away, they start feeling this coupling. Right? So therefore, this at some point they start feeling the coupling, and that's the point basically where you see the violation of the fluctuation theorem. But if you put the confining potential, since this particle cannot go very far away, they are always within this confining potential, and when they are nearby, their confining their interaction is very small because the coupling is very weak. So therefore, the weak coupling they do not see. So that's why when you have that, you do not have the confining potential, you see the violation. Yeah. But mathematically, it's quite interesting actually how it appears basically like when you analyze this, and because this is just a physical argument, but it's I mean there is also parameter regime even when you don't have this confining potential where you see that fluctuation theorem is not violated. But okay, this is some kind of understanding, but okay, it's just, and it's a hand waving understanding. When you have a result, you can argue it somehow, like okay. I cannot hear you, Deepak.
Deepak is muted. Deepak, you are muted.
Okay.
So, okay, so this one, okay, I can go to this, I think Gautam had this thing about the heat, no? I can just maybe just quickly
Yes,
tell you maybe. Yeah. So,
yes, sorry. So I'm back. I got connected.
yeah.
So I was saying that it's not because the variable x1 and x2 get bounded, and so then there is not possible to violate the theorem.
But this coupling is also weak. Coupling is weak. So then when they are close by, they behave as if there is no coupling.
Okay, I see. Okay, thank you.
Right. So you have to take it very far away then only, and that by providing this confining potential. So what you are saying that basically, okay, if you don't provide the confining potential, then there's a time scale corresponding to delta. But if you put a confining potential, then this coupling just changes this time scale by just a short amount.
Okay.
So this becomes just a regular perturbation. Yeah. So I think I had this somewhere. Okay. So this is okay. Let me just tell this thing. So let's consider this. There's a one single particle in water. Okay. And so I can write down the, and there's some kind of external force. So I can just write down the Lanzba equation. So this is just m dv dt. So this is just the external force. So this is the conservative part of the force. And this is the non-conservative force. And the whole thing you call it F. And lambda is some parameter. For example, you might just think of it like a, you are just putting the system in a harmonic trap and you are just changing the trap frequency. So that trap frequency might be described by the lambda. Okay. So and then this eta is a Gaussian force. Okay. So you can write down the distribution of this thing is basically a Gaussian. Okay. So now you just take that equation and you just multiply by v. Okay. So this equation just takes the same equation. And now see this term here. So this term multiplied by v, which is dx dt. So this term basically is this term, so which you can replace by this and this one. So then you see that, okay, this term you replace by, so this term becomes ddt of half mv square. This is basically this and this if you combine, right? Ddt of half mv square gives this term. And this term comes here. So this term you replace with this term, and then you have this another term with v. So you have this extra term, and then you have this term. So now, so you can look at this term as a, okay, so you integrate this equation over time. So you see that this guy is like your total energy. This is the kinetic energy and this is the potential energy. So if you integrate, this guy gives you the total energy change. And this is something your external force. So this is basically the work done by the external force. So now if you just think of it like a first law of thermodynamics, you're changing external energy. It's like this work done plus this amount of heat basically. So this is where you basically how you just get the definition of heat basically. Yeah. And physically you just argue that, okay, this is basically a net amount of force applied by the bath times this velocity. So this is basically the net power injected, and so therefore this is just the work done by the bath basically. But this is still a stochastic force because this depends on its trajectories. And so therefore each of these guys becomes stochastic quantities. So then you can ask about basically the distribution of these stochastic quantities basically. So this one basically you can just think of it like a first law of thermodynamics in the stochastic system basically. So this is a cleaner way to basically define heat basically.
Yeah. Okay, thank you.
Yeah.
Okay, Sanjeev. So I got the definition of heat from this slide as well. So it's right. So in the heat transport problem where you had a source and a sink, so you had two such terms, right? One was QL,
yeah,
and the other one was QR, presumably.
Yeah.
And
yeah. So what we looked at is basically we just looked at one term,
Right.
but in principle we should actually look at the both terms. So what we looked at is just heat coming to the system from just this bath.
Yeah, right.
So in principle, you can look at this heat transfer here, or you can look at it here, or you can look at it here. And
Right.
for each term, basically, you will have a,
So you ignored the cold as the sink.
So what we looked at is basically heat flow to the system from the bath, from the left bath. So we could have also,
So we could, the middle of the
exactly. But using the same formalism, you can also actually look at the heat flow from both the bath to the system, or you can also look at the heat flow divided by the temperature, which from both bath, and that will correspond to the entropy production, basically.
And at steady state, of course, QL has to be equal to QR.
QL doesn't have to be equal to QR. The average has to be equal to Q.
Yes. Yeah. The average. Okay, good. The other thing that it's...
But they can have...
So if you don't
they can have different fluctuations.
Okay. If you don't have nearest neighbor coupling, then the dimensionality of the chain need not be one, right? I mean, in the sense that it could be like a two-dimensional object with one end, tied to a hot something, and some other corner tied to a hot cold something.
Yeah. So what we look at is finally that end is always a single particle in this case.
Right.
But in principle, as you said that, okay, I can have a network of harmonic chain, and then one face I can connect it to the left and one face I can connect to the right. So that's a two-dimensional problem. So that's a problem where actually you can find mu of lambda. This Abhishek and this collaborator, they have looked at this, but this G of lambda calculation becomes extremely complicated in that case. But mu of lambda you can still find there actually.
Okay. And that complication comes in the Green's function, where the phi matrix comes in the denominator. And
because also see in this case, this eta vector and the gamma vector is a bit simpler, right? Because it has only two elements. The gamma is a diagonal matrix with two elements, and the eta also has the same. But they are like this will have, so there it becomes very complicated to find G of lambda.
Right. Okay, thank you. It's a great talk, Sanjeev. I really learned a lot.
Thank you.